Okay. All right, so let me begin. So now we're going to start with a discussion of chapter 7. And in chapter 7, we'll be looking at the different types of chemical reactions. So most of the reactions that exist can fall into the different categories that I'm about to describe right now. So let's talk about the types of chemical reactions. And listed here are 4 types of reactions, but there's actually 5 categories. The 5th one I'm going to mention later on at the end of this chapter. But the first 4 are the ones that are listed here. We have the combination reactions, decomposition reactions, single displacement reactions, and double displacement reactions. All right. And then later on, we're going to learn about a 5th category known as combustion reactions. Okay, so let's talk about firstly combination reactions. What do we mean by combination? Well, a combination reaction is where you have 2 or more reactants reacting to form one product. All right. So hypothetically speaking, if you have reactant A reacting with reactant B, and the product is a combination of those 2, A, B, then that's what we're talking about when we refer to combination reactions. So that's a hypothetical example. I think I have some real examples coming up. So the first type of that type of reaction would be the reaction between a metal and an oxygen to form a metal oxide, such as the one that is shown here. Calcium plus oxygen gives you calcium oxide. Another example here, aluminum plus oxygen gives you aluminum oxide. So these are both examples of combination reaction where you have a metal reacting with oxygen. Then we have a situation where you can have a non-metal reacting with oxygen to form a non-metallic oxide, such as the one shown here, the reaction between sulfur and oxygen to form sulfur dioxide, and the reaction here between nitrogen and oxygen to form nitrogen monoxide. Then we have a situation where you can have a metal combining with some other non-metal other than oxygen. For example, the reaction between potassium and fluorine to form potassium fluoride, and the reaction between aluminum and chlorine to form, aluminum chloride. Okay, so those are other examples of combination reactions. And then we have this example where you have a metallic oxide reacting with water to form a metal hydroxide, such as in this case where sodium oxide reacts with water to form sodium hydroxide. And here's another example, calcium hydroxide reacting with water to form calcium hydroxide. So these are all examples of combination reactions. Here's another one where you have a non-metallic oxide reacting with water to form an oxyacid. In this example, sulfur trioxide is reacting with water to form sulfuric acid. And in the next example, dinitrogen pentoxide is reacting with water to form nitric acid. So these, again, are examples of combination reactions where you have 2 or more reactants combining to form one product. Okay, the second category of reactions we're going to look at are known as decomposition reactions. And in these reactions, it's kind of like the reverse of combination reactions, where you have a single reactant that breaks down to give 2 or more different substances. So hypothetically speaking, here's your reactant AB, and it reacts to form A and B separate. And usually, in fact, in the vast majority of cases, heat is required in order to carry out this type of reaction. All right, so you have to heat AB to get your products so that you end up with your decomposition products. So let's look at some real examples. So in some cases, if you heat a metal oxide, you'll get metal and oxygen, such as in the case of the heating of silver oxide, it will decompose to form silver and oxygen. Here's another example. Now, in this case, a metal oxide is being heated to form another metal oxide and oxygen. In this case, you're heating lead-4 oxide. That's what this is. This is lead-4 oxide, and it reacts to form lead-2 oxide and oxygen. Some carbonates, when heated, will also decompose, as you can see in this case, where calcium carbonate is heated to form calcium oxide and carbon dioxide. And in some cases, hydrogen carbonates will decompose. But in this case, in addition to carbon dioxide, you're going to end up with a carbonate and water as the byproduct. And that's what happens here in this case of heating sodium bicarbonate. You're going to get sodium carbonate, water, and carbon dioxide, all right? And as you can see, in both instances, heat is required. Okay, here's another one. Now this one, actually heat is not required unless you want the reaction to proceed at a very fast rate. Hydrogen peroxide, when heated, will give you water and oxygen. But in actual fact, if you just leave hydrogen peroxide open to the atmosphere, the reaction will take place at a very slow rate, but the reaction will happen, and you're going to end up with oxygen and water being formed. Here's another example. Now, this one requires heat. If you heat potassium chlorate, then you're going to end up with it breaking down or decomposing to form potassium chloride and oxygen. And here's another example. If you heat sodium nitrate, it will decompose to form sodium nitrite, and oxygen. So these are all examples, again, of decomposition reactions. Okay, so let's talk about the third category of reactions in this list. And we're talking here about single displacement reactions. So what happens in a single displacement reaction? Well, as stated here, in a single displacement reaction, one element reacts with a compound to replace one of the elements of that compound. So in other words, if we look at it hypothetically, let's say A is an element reacting with this compound BC, where B or C is an element, then what will happen in this case is that the A will displace the B, right, by combining with the C, and you end up with your products on this side here, all right? So that's what happens in a single displacement reaction. You have one element replacing another, and you're going to end up with new products being formed as a result. So let's look at some real example. One common example that we can see is the reaction between a metal and an acid. Now, this will happen with the more active metals, like the metals in group 1A, group 2A, and group 3A to a lesser extent. But this tends not to happen with other metals, like, for example, the transition metals. In any case, in this particular example, if you take magnesium and you add it to hydrochloric acid, then what will happen very rapidly is that you're going to observe bubbles being formed, and the bubbles will be due to the hydrogen gas being produced. And the hydrogen gas being produced is displaced from the acid. So therefore, hold on 1 minute, the phone is going off. Sorry about that. So as I was saying, what will happen is that the magnesium will displace the hydrogen, and that's why hydrogen is produced here, and the magnesium will combine with what's left, which is a chlorine, to form the magnesium chloride. So that's what happens in the reaction with active metals and acid. You end up with hydrogen being displaced and a salt being produced. Another example is this example right here. Aluminum reacting with sulfuric acid to form aluminum sulfate and hydrogen. So, I'm sorry, somebody keep calling. Okay, so the aluminum is reacting with the acid to form aluminum sulfate and hydrogen. And again, what is happening here is that the aluminum is displacing the hydrogen, and you're going to end up with your products, all right? So that's what happens in single displacement reactions, where you have a metal reacting with an acid to form hydrogen and a salt. So that's what happened in those instances. You can also have a situation where metal will react with water, and it's kind of similar to what we saw in the case of the metal reacting with acid. Again, what will happen is that the metal is going to replace or displace a hydrogen, in this case from the water. The result would be hydrogen being formed in the form of a gas, and sodium hydroxide, or the hydroxide of the metal, will be produced. So in this case, we're talking about sodium displacing hydrogen, and you're going to end up with sodium hydroxide as one of the two products. So that's what happens in this case. The sodium is displacing the hydrogens from water, and you end up with your products. So sodium hydroxide is the product, which is a metal hydroxide. Here's another example. Same thing is happening. In this case, the metal is calcium reacting with water to form the products. Now, the first one is a more vigorous reaction. It happens immediately, and it's a very violent reaction. The one with calcium hydroxide is a much slower reaction, and if you want to speed it up, then you'd have to heat the mixture in order for the reaction to occur. But the same principle applies. The metal is displacing the hydrogen to form the products. Okay, here's another example. Now, in this case, we have a reaction between a metal and water to form a metal oxide instead of a metal hydroxide. In this case, it's iron reacting with water to form hydrogen. And this compound here is a very special compound. It's kind of different. It's actually a combination of two compounds. It's Fe3O4. In some textbooks, they call it iron triiron tetroxide, even though that kind of violates the rules set forth by IUPAC. But let me just explain something about this compound. This compound is actually a mixture of two compounds. One of them is Fe2O3, and the other one is FeO. So it's actually not a mixture, but it's a very intimate combination of these two compounds. This one is iron 3 oxide. This one is iron 2 oxide, right? So basically they're combined with each other to form this compound, which is called Fe3O4. And that's a product when the iron, let me go back to my, when the iron displaces water from this, displaces hydrogen from the water to give you hydrogen and this compound here, all right? So that's what happens in this case. And then in the next example, oh, there's no more example of that one. So this is just yet another example of a single displacement reaction. Okay, now that we have discussed this, we can talk about what is known as the activity series. And this is very useful for basically making predictions about whether or not a particular single displacement reaction will occur. So what's the activity series? Well, basically it's a list of metals. There's one exception, that's hydrogen, which is not a metal, but generally speaking, it's a list of metals in terms of their order of reactivity, all right? So the way they are arranged, as you can see here, is that the metal at the top would be the most active, and then as you go down, the metal becomes less and less reactive, all right? And this is very useful because we can use this to predict whether or not certain single displacement reaction will occur. And the reason why we can do that is because of this statement right here. This statement says an atom of an element in the activity series will displace an atom of an element below it from one of its compounds. So basically what this is saying is that if you have, let's say, zinc, let's say magnesium in a compound, right? And you add sodium to it, then the sodium is going to displace the magnesium from that compound, and you're going to end up with the products being formed. So for example, let's say, let me get my pen here. So let's say you have magnesium sulfate, and you react it or you add to it sodium, right? Then based on the fact that sodium is above magnesium in the activity series, then we can predict that this reaction will take place where the sodium will displace the magnesium to form sodium sulfate, and the magnesium will be formed as well, all right? So basically all you need to do here, from here, is to balance this equation, which means you're going to need a 2 there, and that's it, all right? So that's basically the utility of using the activity series. You can make predictions as to whether or not a particular single displacement reaction will take place based on the positions of the elements, the metals in the activity series. As I said before, hydrogen is not a metal, but it's placed here because we can also make predictions with respect to the reactions of metals with acids based on the activity series. Okay, let me just say also before I leave this page that this activity series here is not the most comprehensive. And I think I may have a more comprehensive list. Let me check and see. Let me go to Canvas and see if I have posted. I don't remember if I posted an activity series here in, there's a tables. Let me go to tables. Oh, yes, it's here. Let me see here. Okay, so here is, let me download this. Come on. Okay, so here is a more comprehensive activity series, right? I think it's a longer list compared to the one that I just showed you. For one, this list has lithium, which is more reactive than potassium, which is not in the list that I showed you here. Lithium would be above potassium, all right? So basically, if there are any problems that you need to solve using the activity series, then this is what you're going to use, all right? Now, I'm going to mention the halogens here because the halogens as a group also forms its own activity series. Okay, I see somebody has a question or, and we're able to, oh yes, you're able to use this table for any future test, yes. So you don't have to memorize it. So you'll have access to that as well. Okay, so what was I saying? Okay, so let me go back to the PowerPoint here. And okay, so let's look at some examples using the activity series to make predictions as to whether or not a reaction will take place. So let's look at this reaction here, the reaction between magnesium and lead 2 sulfide to form magnesium sulfide and lead. A possible test question could be, will this reaction occur? And the answer would be yes, because if you look at magnesium in relation to where lead is in the activity series, you see that magnesium is above lead. So therefore, magnesium will displace lead from lead sulfide, and you're going to end up with magnesium sulfide and lead being displaced, all right? So that's basically how you use the activity series to make these kinds of predictions, all right? Okay, now here's an example where the reaction will not take place. Let's say you're given silver reacting with copper 2 chloride, and let's say you're asked whether or not this reaction will take place. Well, the answer would be no, because if you look at where silver is compared to copper, you see that silver is just below copper right here. So what that tells you is that because silver is below copper, then silver cannot displace copper from the copper 2 chloride. So therefore, we can conclude that no reaction will take place, all right? The other way will happen. In other words, copper will displace silver, but silver will not displace copper because silver is below copper, all right? So those two examples just shows how you can use the activity series to make certain predictions as to whether or not a single displacement reaction will take place, all right? Okay, any questions so far? Any questions? Any questions? Okay, moving along. So let's talk about the halogen activity series. I mentioned it briefly that the halogens themselves have their own activity series. So the halogens, if you remember, are the elements in group 7, right? Starting with fluorine at the top. Let me see if, okay, so starting with fluorine, then chlorine, then bromine, then iodine, right? And what you'll find is that just as how in the metallic activity series where the element at the top will displace the one below it or the ones below it from your compounds, the same is true in this arrangement of, as far as the halogens are concerned, right? So as stated here, the halogen higher in the activity series displaces the halogen below it. So for example, if you're looking at chlorine reacting with calcium bromide, what will happen is that the chlorine will displace the bromine because as you can see here, the chlorine is above bromine in this series, all right? So therefore, that's the reason why we can make a prediction that this reaction will take place where the chlorine displaces the bromine to form calcium chloride and bromine will be displaced, all right? So that's how we can use the halogens to make predictions of single displacement reactions where we have halogens being involved. Okay, so let's talk about the fourth category of reactions known as double displacement reactions. So in a double displacement reactions, what we have is an exchange of partners between two compounds. And this typically happens when you have two ionic compounds reacting, all right? So basically, let's say AB is one ionic compound and CD is another ionic compound, right? So you'll notice what is happening here. There's a switching of the partners where the A will combine with the D from the other compound, and the C will combine with the B from this compound here. So basically, you have A displacing C, and therefore the product of that reaction is AD, and you're going to have B displacing B, and the product of that reaction would be CB, all right? So that's basically what happens in every single example or case of a double displacement reaction. So let's see some features of a double displacement reaction, and the following tend to occur when we observe double displacement reactions. One is the formation of a precipitate. Now, what do we mean by this term precipitate? A precipitate is basically a solid that is formed when two solutions are mixed with each other, all right? And we're going to see some examples of that. Another thing that you'll observe with many double displacement reactions is the formation of gas bubbles, all right? The term we use to describe that, we say that it's an effervescent. That's basically a fancy word for saying bubbles of a gas is being formed. And then the fourth, or I should say the third thing that we normally observe in many double displacement reactions, if you don't see a precipitate or don't see any bubbles being formed, then you actually observe a release of heat, all right? So in other words, the term we use to describe that, we say that the reaction is exothermic, all right? And the fourth and final observation that one would make for a double displacement reaction is the formation of water, all right? So pretty much any one, and in some cases, a combination of two or more of these occurring is what you would observe in many double displacement reactions. Okay, so let's look at a few examples. So the first one we're going to look at is the acid-base neutralization reaction, right? And basically what happens in these reactions is that you have an acid reacting with a base to form a salt and water. So a simple example of this is the reaction between hydrochloric acid and sodium hydroxide, all right? And what we would observe is, as you can see in this equation, is an exchange of partners where the hydrogen will displace the sodium, and that would result in the formation of water, and the chloride will displace the hydroxide, and that would result in the formation of sodium chloride, right? The sodium chloride, of course, will be the salt. So the hydrogen displaces the sodium, the chloride displaces the hydroxide, you end up with these products, and that's basically what happens in a typical acid-base neutralization reaction, all right? Here's another one, another example, same principle. In this case, the hydrogen will displace the sodium again, and the sulfate, which is a polyatomic ion, will displace the hydroxide, and you're going to end up with your products, which would be sodium sulfate and water, all right? So that's basically what happens in every acid-base neutralization reaction. In fact, in all acid-base neutralization reaction, water will be formed, and the other product is basically the salt, resulting from a combination of the positive ion from the base and the negative ion from the acid. Okay, so that's one type of double displacement reaction. Another type of double displacement reaction is one where a precipitate is formed. And this is a very common example of this phenomenon. In this case, we have a solution of silver nitrate mixed with a solution of sodium chloride. So these are two clear solutions, right? And then when you mix them together, you see the spontaneous formation of silver chloride, which would be a solid. So you're going to see a white solid being formed. And you're going to see also sodium nitrate, which will remain in an aqueous solution. In fact, let me see if I can find a video which demonstrates this reaction here. So let me go to YouTube and let me look for precipitation of silver chloride. I'm quite sure there's a demonstration of that somewhere here. Let me see, let me see. Let's see, let's see. Let me see what this one has to offer. Okay, I don't think there's any volume with this, but let me just describe what's happening here. So this person is pouring silver nitrate in a beaker, and the other solution he's pouring now is silver chloride solution. So these are two clear transparent solutions, as you can see. And let's see what happens when they're mixed together. All right, so that's what happens. You get a white solid being formed, and that solid is called a precipitate. So the question is asking, what is the other soluble salt? And we answered that question already. That's the sodium nitrate being formed. Now, let me just describe what this person is doing here. What he is doing, I think it's a he, looks like a he. He's filtering the mixture because what he wants to do is collect the white solid. So we use a filter paper in a funnel. For those of you who plan to do Chem 1, you'll be doing this. And if you plan to do organic chemistry, you'll be doing a lot of this, where you have to separate a solid from the mixture this way. The only issue I have with what he's doing is that the filter paper he's using is too large. The filter paper should not go above the mouth of the funnel. But apart from that, this is the setup. And as you can see, the white solid is deposited on the filter paper, and that will be the silver chloride. And all you have to do from here is to open it up, let it dry, and then, you may need to weigh it to determine the mass and all of that. But that's basically an example of a precipitation reaction. Okay, let me see what it says. Allow the silver chloride to dry. Okay, so that's basically it as far as that is concerned. All right. Going back to the PowerPoint. So, okay, what is this? Let me get this out of the way. Okay, so that's a silver chloride formation from silver nitrate and sodium chloride. And here's another example. Now, in this case, you're mixing potassium iodide and lead-2 nitrate. And again, you're going to get a precipitate. Now, if I remember correctly, this precipitate is yellow in color, right? So you're going to have two clear solutions. If I remember correctly, this is yellow. This is clear, and you're going to get a yellow precipitate. In fact, let me see if I can find a video of that. So precipitation of lead-2 iodide. Let's see if I can find. Okay, here it is.
Easier because students have a lot of
Okay, enough of that. So that is the second reaction that we just discussed here. The reaction between lead nitrate and potassium iodide. I stand corrected. These two solutions are actually colorless, but the product itself or the precipitate itself is yellow, and the potassium nitrate will be the other product here. And again, it's a double displacement reaction where in this case, the lead is displacing the potassium and the nitrate is displacing the iodide, and you end up with those two products, all right? So that's basically what is taking place in a typical double displacement reaction, all right? Okay, another example of a double displacement reaction is the reaction between a metal oxide and an acid. So the products of this reaction would be a salt and water. So this is similar to the neutralization reaction. In this case, we're looking at the reaction between nitric acid and copper-2 oxide. And the products of this reaction would be copper-2 nitrate and water. And what's happening here in this case is that the copper is displacing the hydrogen from the nitric acid. And at the same time, the oxygen is displacing the nitrate. And that's how you end up with your products, all right? Another example here, the reaction between calcium oxide and hydrochloric acid. Again, it's the same idea. The calcium is displacing the hydrogen and the oxygen is displacing the chloride. And again, you're going to end up with your two products, in this case, calcium chloride and water, all right? So that's yet another example of the double displacement reaction at work. And then we have the gas reactions, or the formation of gas reactions. These again are double displacement reaction. Now this reaction here is a reaction that you would not want to do at home or in an enclosed area, because this gas that is produced is very toxic, hydrogen cyanide, all right? It can be formed as a result of the reaction between sulfuric acid and sodium cyanide. Again, it's double displacement where the hydrogen is displacing the sodium and the sulfate is displacing the cyanide. So the results would be the sodium sulfate, which is pretty harmless, but the hydrogen cyanide gas, which is formed, is very toxic, all right? So that's one example of a double displacement reaction, which involves the formation of a gas. Now, the next reaction is another example where, in this case, it's the reaction between ammonium chloride and sodium hydroxide. And as you can see, the products here would be sodium chloride and ammonium hydroxide. So again, this is another double displacement reaction where the ammonium will displace the sodium and the chloride will displace the hydroxide, and you end up with your products where the sodium comes together with the chloride to form sodium chloride. The ammonium will come together with the hydroxide to form ammonium hydroxide. Now, one thing about this reaction is that this is followed by a second step. And okay, it's kind of hard to see, so let me get out of this here. The second step is a spontaneous decomposition of ammonium hydroxide to form ammonia and water, right? So basically, it's a two-step process where the first step is a double displacement reaction, and then the next step would be a decomposition where the ammonium hydroxide decomposes to form ammonia and water, all right? So that's what happens in this particular reaction. Okay, let me go back to the full screen mode. And let me go to the next slide. Oh, and that's it, believe it or not. Well, actually, that's not it, because as promised, there's one other type of reaction that is not included in the list that I gave here. And that fifth category of reactions known as combustion reactions. So let me talk about that. Let me get out of this here. Okay, so there's a group of compounds known as organic compounds, and these are mainly compounds of carbon. Okay, why is this thing not working? Okay, good. All right. So let me erase what I just did here. Okay, so these compounds, they are compounds of carbon, and they tend to contain carbon and hydrogen and oxygen in some cases, and some other elements, nitrogen, halogens, right? But the three main components that you'd find in organic compounds are these three right here. All right. Now, there are a group of compounds, organic compounds known as hydrocarbons. Hydrocarbons. Now, the thing about hydrocarbons is that these are compounds that contain carbon and hydrogen only. All right. Now, the thing about hydrocarbons too is that when you burn them, they react with oxygen from the atmosphere, and the products will be carbon dioxide and water. And we're assuming that this would be a complete burning. The term that we use, of course, is combustion, which means burning basically, right? So if you burn or combust any compound that contains carbon and hydrogen only, it's going to react with oxygen, and the products of this reaction will be CO2 and H2O, all right? So let me give you a couple of examples. So for example, the simplest hydrocarbon is a compound known as methane, all right? When you react it with oxygen, the products will be CO2 and H2O. So now that we have figured out what the products are, all we need to do is balance this equation. So to balance this equation, we're going to need a 2 here and a 2 here, and that would be the balanced equation for this reaction. All right. Let me give a more complex example. There's a compound known as benzene, and the formula for this compound is C6H6. All right. Again, if you were to burn it in oxygen, and if the combustion is complete, then you're going to end up with, again, CO2 and H2O. All right. Oops. Okay, so again, we have to balance this equation. So therefore, we need a 6 here. We need a 3 here. So that's what, 6 times 2, 12, plus 3, 15. So we're going to need 15 over 2 here, but of course, we cannot leave it like that. So we would have to multiply this equation by 2. So we're going to end up with 2 C6H6 plus 15 O2 to give 12 CO2 plus 6 H2O. And that would be the balanced equation. All right. So that's basically how you can write down the balanced equation for the combustion of hydrocarbons. All right. As I said before, you have other organic compounds which would contain carbon, hydrogen, and oxygen. And it turns out that if that's the case, the products also, when you have burning of those compounds, the products will also be carbon dioxide and water. So let me give a couple of examples of that. Let me erase this here. In fact, let me make life easier. Let me lasso this here and delete. Okay, hold on. Okay, so let me go back to my pen function here. Okay, so let's say your compound is C6H12O6. All right, so this is an organic compound which contains carbon, hydrogen, and oxygen. Again, when it's burnt in air, you're going to end up with the same products, CO2 and H2O. And to balance this, 1 minute. And to balance this, okay, we have 6 carbons here. So I would put a coefficient of 6 here. We have 12 hydrogens here. So I'll put a coefficient of 6 here. And then as far as the oxygens are concerned, we have a total of 6 times 2, 12, plus 6, 18 oxygens on the right. We have 6 oxygens here. So I'll put a 6 here to make the total number of oxygens on the left being equal to 18. All right. So that's basically how we determine the products of a combustion reaction when it comes to organic compounds, which contains either carbon and hydrogen only in the case of in the case of hydrocarbons, or compounds containing carbon, hydrogen, and oxygen. In both cases, the products are CO2 and H2O, all right? The only difference between them, of course, is that you have to make sure that they're balanced so that the number of atoms of each element on both sides of the equation would be the same, all right? Okay, so that's basically it as far as chapter 7 is concerned. So as you can see, chapter 7 is a relatively short chapter. Okay, are there any questions you have concerning what we just covered? Any questions? Any questions? Okay, let's move on to chapter 8. Let me get onto this here. Let me go here. Let me close this lecture notes. So what I'm going to do is make sure I publish this. I forgot to publish chapter 6 last time. And let's move on now to chapter 8. And we're going to start chapter 8, but we won't finish it today, of course. So chapter 8 is dealing with the composition of compounds. We kind of talked about it earlier, but we're going to delve into this in greater detail. Okay, so when we're talking about the composition, we said before that we're talking about basically the makeup, right? Especially with respect to mass percentages, the different percentages of the different elements present in the compound. Now, before we get into that, we need to be introduced to some preliminary concepts, and the first of which is the mole concept. So when we're talking about the mole, it's important for several reasons, not the least of which is that in chemistry, we are concerned with small particles like atoms and molecules and so on. So these particles, of course, as you can imagine, are too small to measure on a conventional balance, all right? So for example, the mass of the hydrogen atom given here is 1.673 times 10 to the minus 24 grams. That is, as you can see, a very small number. And obviously, we did not obtain that number by weighing the hydrogen atom. Actually, calculations would have to be involved based on data that was obtained in order to determine the mass of a single hydrogen atom, all right? So as stated here, this is a very, very small number. So that's where the mole concept comes in, as you're going to see later on, because the mole concept helps us to determine or understand or manipulate, appreciate the sizes of atoms and also the sheer size of the number of atoms present in a sample of a substance. Okay, so let's define some terms here. The first of which is the atomic number, right? So the atomic number, and the traditional conventional symbol for the atomic number is Z, uppercase Z. And by definition, this is the number of protons in the nucleus of a given atom of a given element, all right? And each element has its own unique atomic number. So if you consult any periodic table, you'll see that each element has its own unique number. So for example, hydrogen is the only element that has an atomic number of 1. Sodium is the only element that has the atomic number 11. And calcium is the only element that has the atomic number 20, all right? So those are just a few examples of different elements with their own unique atomic number. Then we get to another term called the mass number. And the mass number, by definition, is the sum of the number of protons and neutrons in an atom of an element. Now, unlike the atomic number, the mass number is not very unique, all right? Because it is possible for two identical, well, let me not say identical atoms. It's possible for two atoms of the same element to have different mass numbers. And as we're going to see later on, or shortly, that is because you can have the possibility of two atoms of the same element having different numbers of neutrons. Okay, the next term that we need to talk about is the atomic mass. So the atomic mass is the mass of an atom that is expressed in a special unit known as the atomic mass unit, AMU, all right? And that's because, of course, atoms are very tiny. So it's very difficult to use conventional mass units to express the mass of an atom or a molecule. So that's the reason why we have the atomic mass unit. And the definition of the atomic mass unit is given right here. One atomic mass unit is equal to exactly 1/12 the mass of a carbon-12 atom. So basically what this means is that the mass of a carbon-12 atom is equal to 12 AMU, atomic mass units. And with respect to the relationship between the atomic mass unit and the gram unit, this is the relationship right here. One atomic mass unit is equal to 1.66. We're going to use three significant figures for all purposes here. So it's going to be 1.66 times 10 to the minus 24 grams. All right, so that's a relationship between the atomic mass unit and the gram unit. All right. Now, one important thing you need to recognize here, and this might sound a bit counterintuitive, and that is that the mass of an atom is not exactly the sum of the masses of the protons and neutrons and electrons, right? Now, that might sound weird, but it turns out that when it comes to small particles like an atom and even smaller particles like protons and neutrons and electrons, they tend not to behave the same way that they behave, that regular sized particles would behave. And that's all I'm going to say about this. The reasons for that is a bit, beyond the scope of this level. But for those of you who plan to do general chemistry 2, you're going to learn more about why this is the case. Why is it that the mass of an atom is not the same as the total mass of the protons, neutrons, and electrons? There is a concept known as mass defect, which explains this observation, which, as I said before, is beyond the scope of this course, all right? Okay, so when it comes to expressing large numbers of atoms, we in chemistry and also in physics to some extent require a unit, and that unit is called the mole unit, all right? And I like to refer to the mole unit as something equivalent to the term dozen that we use in our everyday language, right? Because the term dozen means 12, right? If I talk about a dozen eggs, everybody understands that we're talking about 12 eggs. Well, we in chemistry tend to use the mole unit in the same way, but the definition of the mole is a much larger number than a dozen, right? As you can see here, 1 mole is equal to 6.022 times 10 to the 23 of that particular item, right? So the mole concept or the mole unit can literally be applied to anything, right? But of course, in the context of chemistry and physics, as I said before, to a lesser extent, we tend to apply the mole concept to small particles like atoms and molecules and ions and so on, all right? So as stated here, just in case you haven't recognized or gotten the message, that number, 6.02 times 10 to the 23, is a very large number, all right? Very huge number, all right? And there's a special name given to this number. It's called Avogadro's number, named after the famous Italian scientist. Okay, so whenever you hear the term Avogadro's number, you should immediately remember that's referring to this number here, which represents the number of items in 1 mole of that item. So just to give you an idea as to how large a number we're talking about here, if 10,000 people started to count Avogadro's number and counted at a rate of 100 numbers per minute, each minute of the day, it would take over 1 trillion years to count the total number. All right, so that gives you an idea as to the sheer size of Avogadro's number. Okay, so applying what we just learned, Avogadro's number, to elements and compounds and so on. Let's deal with elements first. 1 mole of any element contains this number, Avogadro's number, particles. In most cases, that would be atoms of that substance. All right, so that's basically the relationship between the mole unit and Avogadro's number. All right. Now, another term that I need to talk about here is the molar mass of an element, right? And it turns out that the atomic mass expressed in grams of any element contains 1 mole of atoms, right? So if you remember, we talked about the atomic mass earlier. That would be the mass of an average atom of an element. turns out that when you express that number in grams, then that would be equal to 1 mole. In other words, that mass in grams will contain Avogadro's number of atoms. And we call this the molar mass. In fact, the definition of the molar mass here is the mass in grams. I thought I had a definition here. Hold on 1 minute. Okay, I didn't have the definition here, but I'm sorry. So the definition, let me write this down so that you can have it to refer to. Oh gosh, I can't. Oh, let me do this. Okay, so by definition, the molar mass is the mass of 1 mole of a substance. And that substance could be an element, it could be a compound, doesn't matter, all right? That's basically what the molar mass is by definition. Okay, let me get back to my pointer. Okay, so that's the definition of the molar mass. It is a mass of 1 mole of a substance, and usually that mass is expressed in grams, right? So the relationship between the atomic mass and the molar mass numerically is the same, right? Numerically, the atomic mass and the molar mass of an element are the same. The difference between them would be the units, right? The units of atomic mass is AMU, while the units of molar mass would be grams per mole, all right? So please know the difference between them. So for example, let me see here. So for example, if you go to the periodic table and you look up, let's say the molar mass, or I should say the atomic mass of sodium. So let me write this, hold on, I'm sorry. Let me go to my pen again. So if you look up the periodic table and you look up the atomic mass of sodium, right? Then that would be equal to 22.99 AMU, right? That's the atomic mass of sodium. But the molar mass of sodium, molar mass of sodium would be equal to 22.99 grams per mole, all right? So please know the difference between the atomic mass and the molar mass. Numerically, they're the same, 22.99, but the units will be different. The units of atomic mass is AMU. The units of molar mass would be grams per mole. All right, so with that said, so basically what we have learned so far is that 1 mole of any element contains the same number of atoms as there are in 12 grams of carbon-12. And that number, of course, is Avogadro's number, which is 6.022 times 10 to the 23, all right? So there's a relationship between the molar mass or I should say, the relationship, of course, is established between the moles and the number of atoms for a particular element, right? So that is true for any element, such as hydrogen, where 1 mole of it contains Avogadro's number of atoms, 6.02 times 10 to the 23, or even for a molecule, same thing, 1 mole will contain 6.022 times 10 to the 23 molecules. Or in the case of sodium, 1 mole of sodium will contain the same number of sodium atoms. Same is true for iron. Same is true for a molecule like benzene, and so on and so forth. So 1 mole of atoms contains Avogadro's number of atoms. 1 mole of molecule contains Avogadro's number of molecules. 1 mole of ions contains Avogadro's number of ions. So 1 mole can apply to all of these particular particles, all right? So just to remind you, I just said so a while ago, and I'm going to say it again. The molar mass of an element is its atomic mass expressed in grams per mole, all right? And it contains, that molar mass per mole contains Avogadro's number of atoms of that particular element, all right? So for example, hydrogen has, let me get out of this here again, get back to my pointer. So hydrogen has an atomic mass of 1.008 AMU. The molar mass is going to be 1.008 grams per mole, and therefore the number of atoms present in 1 mole will be 6.02 times 10 to the 23, right? And that is true for magnesium in terms of the number of atoms per mole, and for sodium. The difference, of course, would be their molar masses. The molar masses are different. 1 mole of hydrogen will have a different mass compared to 1 mole of magnesium, which in turn will have a different mass compared to 1 mole of sodium. All right, so that's basically the difference between these elements. Their molar masses will be different, but the number of atoms present per mole will be the same. All right, okay, so let's look at some examples of problems that we can do based on what we have just learned. So let's say you're asked this question: how many iron atoms are contained in 25.0 grams of iron? So the way I would do this is I would start off with the 25 grams, 25.0 grams, and then, well, okay, you know what? Let me do this first. I'm sorry. Let me erase this first. Okay, and let me go back to my pointer to get a pen. And you know what? Let me get, I think this might be a bit clearer. Okay, so what I'm going to do is I'm going to start with the grams of iron and then convert it to moles of iron. Okay, something is wrong with my pen here. And then convert that to atoms of iron or iron atoms, all right? So in order for us to do this, we have to basically multiply by 2 conversion factors in series. So I'm going to start off with 25.0 grams of Fe, and we're going to convert that to moles, which means that the conversion factor is going to have 1 mole of iron here above as a numerator, and down here would be the molar mass. Now, I don't remember what the molar mass of iron is, so I'm going to look it up in the tables, chemistry, download, or I can just look at it from here. Iron, okay, 55.85 grams. So let me go back here, and let me go here, get back my pen. So the molar mass of iron is 55.85 grams of Fe. So this unit will cancel out with this unit. And then the next step is to convert from, as I said before, moles of iron to iron atoms. And this is where Avogadro's number comes in. 6.02 times 10 to the 23 Fe atoms would be the numerator. And down here, you're going to have 1 mole of Fe, so that this will cancel with that. And all you have to do is some number crunching. So let me do this on my calculator. And please, folks, do the calculations along with me, because I could be totally wrong. Just to check and make sure that I'm doing the right thing. So according to my answer, and the answer would have to be rounded off to 3 sig figs, it's going to be equal to 2.69 times 10 to the 23 Fe atoms. Whoops. Okay, so that's basically how you would do that example. All right. Okay, any questions about this example? Any questions? Any questions? Okay, let's move along. I think I have another example lined up. Okay, so in this case, it's the reverse. They gave you the number of atoms of sodium, and they're asking for the mass. Okay, so basically you're given the sodium atoms, and what I would do is first convert that to moles of sodium, and then I'll convert that to mass in grams of sodium. All right, so I would start off with the 3.01 times 10 to the 23 sodium atoms. And then I would multiply that by, so the numerator would be 1 mole of sodium. And down here would be Avogadro's number, which is 6.02 times 10 to the 23 sodium atoms. And then the next conversion factor, oh, by the way, this is going to cancel out with that. And then the next conversion factor would be 1 mole of sodium down here, and the molar mass of sodium, which is 22.99 grams of sodium. So the mole unit will cancel out here and here. So let's see what this gives. 3.01 times 10 to the 23 divided by 6.02 times 10 to the 23, and then multiply by 22.99. And according to my answer, when rounded off to 3 sig figs, the answer is 11.5 grams of sodium. So that's basically how that example will be done. Okay, any questions about this example? Any questions? Any questions? Okay, moving along. I think I have another example lined up. Now, this one is much easier because in this case, they gave you, they gave you the moles of tin, and you're asked for the mass in grams of tin. And the reason why this is easier because you can actually go directly from moles to mass using the molar mass. So let's do that. You're given 0.365 grams of tin, and then you have to multiply that by 1 mole of tin, and down here would be the molar mass. So let me look up the molar mass of tin. Where's tin? Tin. Tin is here. Okay, so the molar mass of tin is 118.7. So down here, we're going to have 118.7, 118.7 grams of tin. So that goes with that. So 0.365 divided by 118.7. And according to my calculation, this works out to be equal to 3, whoops. Oh, wait a minute. I made a big error here. I'm sorry. Let me scratch this out. They didn't give you the grams, they gave you the moles. So this should be 0.365 moles of tin. And then I multiply by 118.7 grams of tin over 1 mole. All right. So what I was doing up here is totally wrong. So let me do that calculation. 0.365 divided by 118.7. So, oh, wait a minute. Multiply by, what am I doing? 0.365 multiply by 118.7. Okay, so according to my answer, I got 43.3 grams of tin. All right. So that's basically how that is done. Okay, any questions about this example? Any questions? Okay, moving along. Okay, I think this might be the last example. Let me check something here. Okay, yeah, let's make this the last example. Okay, so this question says, how many oxygen atoms are present in 2.0 moles of oxygen molecules? Now, this question, you have to be very careful in doing it, because, let me see if I can underline the important part of this question here. Yeah, use a different color. Okay, you'll notice the question says how many oxygen atoms are present in 2.00 moles of oxygen molecules, right? Very important. So let me change my ink color here, back to black. So basically, you're given 2.00 moles of O2, and you're asked to find the number of O2 molecules. So in this case, what you'd have to do is convert from moles of O2 oh shoot, I just realized something. Okay. What I should have done here is this should be moles of, I'm sorry. Okay, for here, this should be moles of O2 atoms. And the question is asking for the amount of oxygen molecules. So I'm going to start off with 2.00 moles, shucks, 2.00 moles of oxygen atoms. And the first thing I would do is I would convert that to the number of oxygen atoms. So basically, I'll be using Avogadro's number, where that number will be placed up here, times 10 to the 23 O atoms. And down here, I would have 1 mole of oxygen atoms. So that this will cancel out with this. Then the next step is where I convert from atoms to molecules. And if you look at the molecule, the formula for oxygen molecules, O2, what that tells you is that for every 1 mole of O2 molecule, you have 2 oxygen, I'm sorry, for every 1 oxygen molecule, you have 2 oxygen atoms. I'm sorry about the mistakes I'm making here. Looks untidy. So what's going to happen is that this is going to cancel with this. And then all you have to do is your number crunching. So let me do that now. 2 times 6.02 times 10 to the 23 divided by 2. And that gives you 6.02 times 10 to the 23 molecules. 6.02 times 10 to the 23 molecules. All right. And that's basically, and this will be molecules of oxygen, by the way. And that's basically how that is done. All right. Okay. Any questions about this particular example? Any questions? Any questions? Okay, so that's basically it for today. So before you leave, let me let you know exactly what I expect you to do as far as assignments are concerned. So we just finished chapter, hold on 1 minute. We just finished chapter 6 and part of 7. So for now, no, what am I saying? Hold on 1 minute. We finished chapter 7 and we just started chapter 8. So that means that for chapter 7, there's only one assignment, and that's assignment 15. All right. So let me publish that now. All right, and let me check out chapter 8 here. Okay, I'm not going to assign anything from chapter 8 quite yet, because I think chapter 7, the assignment for chapter 7, which is assignment 15, is pretty long. So basically, that's your assignment that you need to complete. Now, let me see something here, because I think I remember I assigned chapter 14 to you guys, right? Yes, okay. So I don't recall giving a due date. So let me check this out here. I must have given you a due date if I assigned it, but sometimes okay. So this is due September 17th, which is this Friday. All right. So make sure you do that. And what I'm going to do is I'm going to let me do editing here. I'm going to assign assignment 15, and that will be due also on the 17th as well. All right. Let me publish it. Let me make sure it's ready for the upload of your documents. Yes, it is. Okay. So those are the assignments that will be due on the 17th. All right. So again, make sure that it's saved and uploaded as a PDF document. Make sure that you do it in blue or black ink, and all that other good stuff. All right. So that's basically all I have for you today, unless there is any additional questions you have to ask.
I have one just about how we're scheduling our tests for the testing center. I was trying to do it now, and I didn't see your name under the list of like professors, and I don't know why.
Well, I didn't know that there was supposed to be like a list of professors' names, because in the past, what I would do is send a test over there. I think they've changed how they do things over there a bit. So I'd have to call over there and find out exactly what the new procedure is. So I'll find out all of that information and get back to you on Wednesday.
Okay, because it asks me, like when I try to make an appointment for it, it asks me what kind of test I'm taking, and the only one that really applies to this class is the option for a teacher here at CF, and then it asks you to put in a specific professor, and I just didn't see your name.
Okay, I'll have to inquire about that, because that must be a new thing. I never heard of that before, to be perfectly honest. So I'll make inquiries about that and get back to you guys on that. All right. Any other questions before we leave? We have 1 minute left. Okay, so that's it for today. So I'll see you guys on Wednesday. All right, so take care. Enjoy the rest of today.